Hi everyone, hope you're doing well. In the present lecture, we'll talk about this important problem in quantum mechanics, which is the Gaussian wave packet, the quantum dynamics of the Gaussian wave packet. There are some important problems in quantum mechanics, and just to enlist a few of them, I personally include the Gaussian wave packet because it enlightens a few features of quantum mechanics. Potential wells are very important from a theoretical perspective and also for a few applications. It's a very didactical problem, a pedagogical problem in quantum mechanics. Of course, the harmonic oscillator, which is the starting point to deal with annihilation and creation operators. There are operator methods which can be applied here. And also quantum mechanics started with the problem of harmonic oscillators, which was uh, properly addressed by Planck. And of course, the hydrogen atom, but this problem I will not talk about. And in the present lecture, we will be focused on discussing the Gaussian wave packets, all right? Quantum dynamics of a Gaussian wave packet. So a, a Gaussian wave packet, this is the problem. Quantum dynamics of it is some probability distribution for a particle which starts with the following field distribution, all right? So this is the Gaussian. Psi at time t equals to 0, depending on x, I will just use one dimension here, and this integral, which will appear constantly here, is very important for the purposes of this lecture, is equal to some constant a times the exponential of minus x squared divided by some a constant, or perhaps better to use an x not squared here. This is a Gaussian packet at time t equals to 0. You can also make it move, but if you want to make the Gaussian move to some direction, it's like considering some kinetic energy from the start. It will be given by some imaginary factor relating to some initial momentum, some average momentum, P naught divided by h bar. So if you want to make this Gaussian wave packet move to the positive direction in the x-axis, you plug in here a plus sign, and if you want to make it move backwards in the x direction, you can plug in here a minus sign, but we'll be concerned with a static Gaussian, all right? So if you plot the Gaussian, you'll find this thing here as a function of x. You can plot the modulus squared. It's the probability, the density probability of finding a particle as a function of position. Of course, if you include this factor here, it doesn't change the probability distribution at time t equals to 0. So at time t equals to 0 here. But as time passes, it changes things a little bit. So after we perform all the calculations, neglecting the factor or not including this factor to be precise, you can do the math including a propagating wave packet. So this is a static no, but it's a wave packet which has an average momentum of 0. If you include that other term, the average momentum of that packet will not be 0. It will be centered at p0, all right? So this has momentum, an average momentum equals to 0, this packet here, all right? This is the average of momentum. If you insert the other term, you translate in momentum coordinates to a value of p0. Right? This is a Gaussian. It has an amplitude of a at x equals to 0, and it goes like the bell curve, or it does as it must. This delta of x here is proportional to this number here, this x naught here. So the uncertainty in finding the particle is proportional to this value of x naught. You can calculate that. You can calculate the average of x. We will find that it is 0, right? You can calculate that term, and you can calculate this average of x squared, and you'll find that it is proportional to the number x0, all right? X0 squared, to be precise, is proportional to that number, all right? So you can calculate the variance and the standard deviation. So it's related to this um, width, and this width is proportional to this number here for the Gaussian, all right? Of course, any function can be, any function of position can be written in the position basis. So the state which we are talking about, the initial state of the system is this psi 0, which we can, of course, expand by introducing here the identity matrix, or the resolution of the identity in terms of the position basis. We know this is just the unit matrix, or the identity matrix, times psi of 0, and this factor here, when you calculate this factor here, this is just the components of this vector in the basis of position, and this is some amplitude a, some value which can be easily determined, exponential minus x squared divided by twice x0 squared. So our starting function, the physical state, this is the physical state. I hope you can see what I'm writing here. Physical state of the system at time t equals to 0 corresponds to an integral over dx from minus infinity to infinity. We are considering only one partial dimension. This is the value of the function in the direction of that x. All right, this is exactly what we mean by that. If you project the x here, if you project this to some value of x, you'll find a Gaussian distribution. All right, so this is the probability for finding the system. All right, this is at t equals to 0. So this is the initial condition. This is the state which we are dealing right now. But let us state the problem, right? Let us state the problem. Well, of course, we can calculate the value of A. So if you integrate the psi 0 squared, let's do it properly. So if we project psi 0 onto itself, it must be unity. You can plug in here the resolution of identity in the position basis. All right, so this is the identity from minus infinity to infinity, and psi 0 here. Of course, this integral goes from minus infinity to infinity, and this just produces psi 0 projected onto x projected onto psi 0, and this is just the integral with respect to the variable x of the modulus squared of this function. This is just the Gaussian. You will find the constant here, a squared, an integral over dx from minus infinity to infinity of the exponential minus x squared divided by x naught squared. And you, as you can see, if you inserted some average for the momentum which is non-vanishing with that exponential term of this form here, it doesn't change anything because the modulus washes out this term from the equation. So the amplitude of A doesn't depend on that factor, all right? So here you can use this result here, and you'll find out that A is 1 over x squared, and you'll find A squared, well, to be precise, this here is equal to square root of pi divided by A, all right? To be correct. And in this case, we'll find out that B in this integral is 0, so this exponential goes to 1, and you'll find here the square root of pi divided by the A factor here, which is 1 over x0 squared. And this must be equal to 1 because of the proper normalization of the function. So you can find out what is the value of A. So this corresponds to A squared square root of pi x0 squared. And of course, you find out what the value of A is. This capital A is the square root of that value. So this is pi x0 squared to the 1/4. All right. This is the value of A. So now we have a proper normalization for our initial state. All right. Initial state. Let me write the initial state here. Psi 0 of x in terms of components of the vector, right? This is projected onto the basis of position. The initial state corresponds to a value 1 divided by pi x0 squared. The A is the inverse of that factor, to be precise, because it's the square root of the square root. And the exponential here, this is our initial state. All right. I hope you can properly see the factors here. And notice that the wave function, as it must be, has units. The units here in the international system of units is 1 of this over the square root of meter. So it's meter to 1/2. All right. Why is that? because this exponential has dimensions of nothing. It's in non-dimensional quantity. Pi is non-dimensional also, and we have x naught squared, which has units of length squared, but you take the fourth root of the equation, so it has meters squared to 1/4, so meters to 1/2. And that's what we need because the amplitude of psi 0 squared corresponds to the density, the probability density, which must be measured as 1 over the volume. And the volume in one dimension is just a length. If you were talking about two dimension, it will be meter squared, and in three dimensions it will be meter cubic meters. So this would correspond to cubic meters to half, or 2 meters squared 1/2 for the amplitude. But we are dealing with just one dimension of space, and this quantity here is measured in 1 over meter. So if squared is 1 over meter, of course the square root of this quantity is meter to the minus 1/2, to be precise, all right? Because this is 1 over meter squared. You take the 1 over 4th, all right? So this is the unit of the wave function. This is correct unit of measurement. So just to remember, meters to the minus 1/2. Okay, this quantity here is after you do the math, will give you the correct units. So what is the problem we wanted to solve here? So uh, considering a free particle, which means potential energy depending on x is equal to 0. There are no potential energies. The particle is free. There are only kinetic energy terms. Considering a free particle in one dimension with an initial Gaussian distribution, find the evolved state in time. And so let us find this object here projected onto the basis of x. So we are trying to solve this problem here. Okay, this is the problem. We are willing to find out what is the evolved state for a Gaussian packet. All right, so we have a Gaussian initial distribution, we have a free particle. What we will find out when this time is evolved, this state is evolved. All right, this is the problem right now. So what we need to do is to solve for Schrodinger's equation. So as a matter of fact, we can just remember that for a free particle, non-relativistic particle, it could be included into the statement. Considering a non-relativistic free particle, you have the Hamiltonian operator is this thing here. All right, this is the Hamiltonian operator, which with the replacement, if you remember properly, this operator represented in the basis of position is just minus I h bar this partial derivative. So this corresponds to the minus h bar squared divided by twice the mass, second order derivative, d second to the dx squared. All right, so this is the second order derivative. This is the operator for a free particle. And the Gaussian wave packet is not an eigenstate of the Hamiltonian, because the Hamiltonian is depending only on momentum operator. So, as you can see, if you remember, so remember that the commutator of position and momentum in the x direction, which I will omit here the subindex x because there is only one dimension. So this commutator here is equal to I h bar. So position and momentum do not commute in quantum mechanics. All right. If you had a classical particle, okay, there is a position function of time, there is a momentum function of time, there are only functions, but here position is one operator, momentum is other operator, and they do not commute, all right? They pertain to distinct basis representations, and they are incompatible, they do not commute. So, in this problem, for the present problem, momentum commute with the Hamiltonian because the Hamiltonian just depend on the momentum operator, but position and the Hamiltonian are incompatible. So if you write a state which in this case is represented by something like this thing here, it is not an eigenstate of momentum. You can do the math and you find out. If you multiply your, if you apply your momentum operator to this thing here, you'll find that this is distinct from some value, some b value here times the state. So this is not an eigenstate of momentum. In our initial state, not an eigenstate of this operator. All right, our initial state of the physical system is not in an eigenstate of momentum. All right. Well, so what we can do, we can calculate the evolution operator. There are many ways to do that. So here we will find out the solution making this thing here. We will use the basis which solves the Hamiltonian, and this is the basis of the momentum operator. So we have momentum applied to some of its eigenstates corresponds to an eigenvalue times the eigenstate, and the Hamiltonian, because it commutes with momentum, has the same eigenstates. So the Hamiltonian applied to one of the eigenvalues of the eigenvectors of momentum just produces the eigenvalue squared divided by twice the mass and repeats the eigenvector. So at the same time, the momentum basis, the basis of momentum, diagonalizes both the momentum operator and the Hamiltonian. Why is that? Because in the present case, in this case, they commute. And if they commute, that's all right. The same basis diagonalize both operators. But the momentum basis or the momentum eigenstates don't diagonalize the position operator. All right, this is a very important issue. Well, if you want to calculate some function of time, this is the function psi of t. You just apply the evolution operator to the initial state. All right, that's what you can do. It's a function of time t. All right. Well, you can see in many textbooks the equation you willing to solve is this one. All right. So I'll write it here just for the sake of reference. You are trying to solve this. The Schrodinger equation in component language, which has I h bar time derivative of the function here corresponds just to momentum operator here, second order derivative of that function with respect to position, because there are no potential energy depending on position. So this is the equation we want to solve. We want to solve this equation. So this is the Schrodinger equation. This is the Schrodinger equation. In one dimension for space. Of course, time is already there. So it's a 1 plus 1 dimensional equation because you have time and space. But with respect to just considering just the number of space dimensions, it's one dimensional equation for space. The Schrodinger equation in one dimension and potential energy equals to 0. So this is the Schrodinger equation for a free particle. All right. So Schrodinger equation for a free particle. Well, free particle being described by a quantum mechanical formalism. So a particle in classical physics is described by a classical field in quantum mechanics. What is this field? Is the field satisfying Schrodinger's equation. Notice also that this Schrodinger equation is the same as a diffusion equation in non-relativistic case, but if you just eliminate the imaginary unit from here and you multiply all the equation by minus I, you'll find out that your diffusion coefficient is purely imaginary. So the Schrodinger equation in a non-relativistic problem is a diffusion equation with a purely imaginary diffusion coefficient. It's the same equation, but with a complex, or as a matter of fact, purely imaginary diffusion coefficient. All right, this is just a curiosity for now. But we are willing to solve the problem using this formalism here. So what we do, we know that the evolution operator is just the exponential of minus I, the Hamiltonian times the time factor divided by h bar. And we already have this operator, so this is an exponential, which if you are willing to represent this operator, the Hamiltonian operator, in the basis of position, it is a second order derivative, and here you have an exponential, so the exponential can be expanded in Taylor series, and you'll find out no derivatives for one plus second order derivatives, fourth order derivatives, and so on. But we will not use the position basis here. So you plug in the Hamiltonian, The Hamiltonian is momentum operator squared divided by twice the mass. The h bar was already there, times t here. This is the evolution operator for our problem. All right, we will use operator methods here. It's very more efficient to solve this equation here. All right, we are solving this equation with a given initial condition. All right. So what we can do now, we represent the evolution operator, which is a function of time t. I guess you're seeing what I'm doing there, by multiplying this with the identity matrix, which can be performed to the right or to the left in this case. Okay, so let me write it here, minus I p squared. This is the operator divided by twice the mass, h bar, times t. And I'll plug in here the resolution of the identity, but in the basis which diagonalize momentum. So from minus infinity to infinity, this is the completeness relation or the resolution of identity in the basis which diagonalize the Hamiltonian, which is the same as the basis of momentum operator. All right? And this is an operator here. When it acts, when this operator acts on one of its eigenvectors, on one of its eigenstates, it just reproduces one of its eigenvalues. So this is an operator. Now it's just a number here. Previously, it's an operator. If you're considering the basis of position, it's a derivative, a second order derivative is proportional to second order derivative. But since I am using the basis which diagonalize that operator, when it acts on its own basis, it just produces the eigenvalue here times t, not squared, just t, divided by twice mass h bar, and now we have this thing here. All right, this is the representation of the evolution operator. Of course, it is very clean now. It's easy to do the math with this operator. So this operator here in this form solves Schrodinger equation, but in place of this psi here, it solves for the evolution operator. All right, and of course here you would replace the second order derivatives by p operator. All right, squared. So just remember this operator here. You can write down on paper. I'm sorry, but the board is a little bit small, so I need to just erase a few of the equations. And now we have psi of t is equal to the evolution operator applied to the initial state, which is just a formal equation as for now. But let us see what happens here. So psi of t corresponds to this thing here. So the integral from minus infinity to infinity, integrated over all the values of momentum. This is just a number now, value of p, twice the mass h bar, p, external product here, but it projects onto psi 0, all right? So this is the time evolved equation. And now, as you can see, you have an integral from minus infinity to infinity the exponential of minus I p squared, the time twice the mass h bar, and this value here, this thing here, is just the components of the wave function represented in momentum space, all right, times p times the momentum eigenvector, all right. So of course, in the end, we can just, to find out what is the value at a given position, we just project this thing here, and what you find is the following equation. When you project x onto p, this is just a number, which you already know what it is from definitions. This is the psi tilde of p, because this is just the initial state represented in momentum coordinates, and the exponential here, which is just a function of momentum. All right, this is what solves that equation. All right, this thing here solves that equation. Right, you can just plug in there and you find out it solves that equation. But first, we need to remember what is this thing. X, p projected onto x is just a representation of a momentum eigenfunction in the position basis, but it is just also the transformation coefficient from one basis to the other, and we already know what it is. It is just exponential of imaginary times p times x divided by the h bar, and it's normalized accordingly to this number here, twice pi, and you plug in some h bar there. I am using the same convention as Sakurai. There are other conventions, but you need to renormalize some integrals there. So this is it. The momentum state projected onto the basis of position just corresponds to this thing here. We already encountered that in previous lectures when we talked about Fourier transforms. All right, so that's it. And now we need to find out what is this object here. Because we need to plug in here this value. All right, so the evolved state is already computed if we know what is this object here. So just remember this thing here. Just remember that. So given this initial state, we can project it to the position basis. So the x here, which is this object here, and we already know this is 1 divided by twice pi x0 squared, I guess, if I, or just pi factor here. It's just pi factor here, 1/4, right? The exponential, right? The exponential here, which is just this object projected onto x. And if I project onto the basis of momentum now, this is just a Fourier transform. right? That's it. I guess you can clearly see what I'm doing here. So now I project onto P. I'll find out this function, which is this object here, is just the Fourier transform of this thing here, because this is the complex conjugate of that number. All right, that's it. Let me rewrite this thing here. So psi of x and p. Let us just replace this object here. It's easier to do. Right? So we'll find out this is exponential. This must be a complex conjugate minus I p x divided by h bar and divided by square root of 2 pi h bar. Right? This is it. This is what we have here. Right? So this equation can be promptly solved. It can be solved using the result, right? Because you can find what is A, what is B, the other things are constants. So you'll find out the constants here. Let us put it in front of the equation. And now we have square root of pi divided by the A factor, which is 1 over 2x0 squared. So 2 pi x0 squared, right? If I did it correctly, they're just a constant. And the exponential, we need to plug in the b factor, which is minus I p h bar, because we are integrating over dx. So find out minus is plus. When you square it, the imaginary gets a -1 when squared, p squared, so p squared over h bar squared, right? Because the h bar is already there. Four times the a value here, which is 1 over 2 x0 squared. So 4 times this value, you get 2 divided by the x naught squared. So number 2 here and the x squared there, right? So that's it. This is the value, and you can plug it into here, onto here, right? So you must integrate from minus infinity to infinity over momentum states, over momentum values. That thing is just a bunch of constants. Let me let me let me rewrite these constants as some value. So all these things here, call it b. So b, it doesn't matter because it's just a constant. All right, some b exponential of I p x divided by the h bar, which is this thing here. All right, this thing here corresponds to this exponential here. This exponential was already there. And that other exponential we must now introduce, which corresponds to this value here, x0 squared, p squared divided by twice the h bar squared. All right, I guess you can see there. And now we have another Gaussian integration, right? So this is what makes Gaussians very interesting to do calculations, because when you integrate one Gaussian, you find out another Gaussian. And when you transform by Fourier transformation, the Fourier transform of a Gaussian is another Gaussian. Makes the problem very easy and interesting to do the math. So right now, remember this factor here, and now this is the solution which we are wanting. So this is the P, which corresponds to a bunch of numbers there, right? So you have a square root of pi x0 squared, and here you have a square root of a square root. You can find out what really really happens in the end. And this square root of 2 cancels out this square root of, as a matter of fact, this 2 pi here cancels out this 2 pi here, and you find out something like this: x0 divided by h bar, the square root of h bar, twice the pi is cancelled out. You'll find out this factor here, pi x0 squared over 1/4, right? This is the b factor out there, times. Now you need to integrate this Gaussian here, and you'll find the square root of pi divided by the a factor here. The a factor here is all the terms multiplying p squared, because multiplying the squared integrand variable, right? Integration variable to be precise, and this corresponds to x0 squared divided by twice h bar squared. It accompanies this term here, and plus the imaginary times t divided by twice m h bar, right? I guess this is all for the a factor here, right? And the exponential corresponds to minus, because the b factor is I p divided by h bar x, and now the b is I x divided by h bar. I squared is minus x squared h bar squared. You'll find out x squared h bar squared, and you need to insert here four times the a, but four times we have a two factor here for both terms, so we can just put it into evidence. 4 times 1/2 is just twice the h squared here, because it's h bar. It enters here squared, twice h bar squared, x0 squared divided by the h bar squared, plus imaginary unit times t divided by twice the mass h bar. So this is the solution of our problem. And we can perform some more simplifications here. So psi of x and t corresponds to some, if we normalize it properly here, we can eliminate that term, and if we just use a little bit of math here, we can perform that. It's just 1 over pi x0 squared to the 1/4, and now we have this other square root. We have a pi factor here divided by a x squared. We can plug into the squared factor here, this term here. So pi x squared divided by twice the h bar squared plus it over 2m h bar, and this h bar here we can insert into the integral here also. And this exponential here is minus x squared, and this h bar here we can multiply all the terms, so x0 squared plus I times t times h bar, because it cancels out this other factor, divided by twice the mass. And now you can do all the calculations to demonstrate that this term here just corresponds, or has, this term here has unit of length squared. It is time seconds multiplying joules times second divided by kilograms. Here you can show it has the dimensions of meters squared in the international system of units, right? Also, if you consider the time t equals to 0, for time t going to 0 here, you will find out the initial, just the initial, I guess I've forgotten some extra square root of 2 pi h bar in some place here, but doesn't matter. At time t equals to 0, it must go to psi 0 of x. So you can find out what is missing from the equations here. So let us see what is happening now. So at time t equals to 0, what we have found here, this exponential is okay, minus x squared twice x0 squared. Here time cancels out. This factor is already there. This must be there because it's the a of the initial solution. And this term here, the x0 cancels out, time t cancels out, but we have a factor of 2 pi h bar. So we need to divide it by here. We need to divide by 2 pi h bar. So when we divide it, it properly gives you the correct answer. This h bar becomes squared, and this factor of pi cancels out here, and you have it twice that term, right? So then you will find out this thing here. This is the initial condition. We are just checking if our solved equation at another instant of time just corresponds to the initial state in the limit of time t going to 0, right? And this is it. This goes to 0 as this is go to the initial state as we let time t go to 0, right? So this is it. This h bar gets squared here. This factor of pi gets cancelled out. This factor of 2 accompanies this term here, and that's all right, I guess. We didn't miss anything. All right. Well, now we need to check out what happens here. I'm looking at the exponential factors. Of course, time t appears also here, but just look at this exponential here, and when you take the squared function at time t, you'll find out the distribution or the probability density for finding the particle, and this is proportional to the exponential of minus x squared divided by x0 squared. And if you multiply this thing by the complex conjugate here, you find out x0 squared minus it h bar divided by twice the mass. You'll find just a real number in the denominator, but here you need to multiply it also by the complex conjugate, so you're multiplying by 1, of course, and you, in modulus, you eliminate the imaginary part, so of course you have the modulus of this thing here also, but you find x0 squared here. This factor of 2, when you square, cancels out. X0 to the fourth power plus time squared h bar squared divided by 4m squared. All right, and also you can divide the equation. It's proportional. The proportionality factor x0 squared plus time squared h bar squared 4 times mass squared x0 squared. Notice the Gaussian here. If you calculate the variance of this Gaussian, it grows with respect to time. So this, let me just look at the Gaussian term, because the amplitude is also varying with time. You can do all the math, but notice the exponential factor here. The exponential factor here, you have a delta of x, let me call this delta of x squared equals to x0 squared plus time t squared h bar 4 times the mass of the particle and the initial width of the Gaussian. So at time t equals to 0, of course, rho xt is proportional. The constant of proportionality here I'm not very interested in, but it's just minus x squared divided by x0 squared or x naught squared. This Gaussian here compared to the I can write it as something like this. The variance squared there, all right, and this variance squared now corresponds to this function. It changes with time. It becomes larger as time grows. So the delta of x, as a matter of fact, corresponds to this thing here. And for very large time t, if this factor here is much larger than this previous one for x0 squared, much less than t squared h bar squared over 4 times mass squared x0 squared, this delta x is approximately given by h bar time t twice the mass x0. All right, this is what you'll find out as time evolves if we perform the calculations correctly. So as you can see, as time grows, the Gaussian becomes larger, but the amplitude, which we are not considering here, becomes smaller, because for any instant of time, if you integrate this thing squared over the x from minus infinity to infinity, this must equal to unity. All right, so this is equal to 1, and you can calculate the free factor here just for the probabilistic distribution, just calculating this integral here. You can find out what is that constant. Apart from a phase factor, that it's not a constant, it's a function of time. You can find out what is the proportionality factor here just to ensure the probability distribution when integrated out over all the x, which means the particle is somewhere in space. It must have a probability of unity. So as time passes, the variance gets higher and higher. Of course, it's a very interesting issue in quantum mechanics. And if you plot a graph of this thing, the modulus or the distribution, the modulus of function squared, you'll find out that at time t equals to 0, you have a Gaussian e to the minus x squared divided by x0 squared is proportional to that term. And as time passes, the Gaussian becomes larger and larger, and the amplitude will decrease. The peak doesn't never changes. It's always at t at x equals to 0. But as time grows, the Gaussian just relax. The uncertainty in the position of the particle becomes higher because this delta x becomes for larger times becomes proportional to time. So for larger times, the uncertainty in the position of the particle becomes higher and higher. All right. So you don't know where your degree of uncertainty in having the particle somewhere becomes higher. That's an important issue. At time t equals to 0, you have some region where there are most of the probability of finding the particle, which corresponds to some extent proportional to x naught. All right, this is the region where you most probably can find the particle. But as time grows, the uncertainty, which is this width of the Gaussian, becomes larger and larger. All right, this is a very interesting problem. And you can calculate some things like the x and the p and the delta of x properly, right? You can calculate these things. Of course, the x squared value, you can calculate all these things, and you can calculate delta x, delta p, and you can show that at any given instant of time, this for sure satisfy the uncertainty principle, which means delta x, delta p is larger than the h bar over 2, right? This is at least equal to h bar over 2, right? This is very important problem in quantum mechanics, and you can show that. Well, now let me just make some connection to finish with this interesting problem in quantum mechanics, which is the connection with optics. There is a so-called Paraxial approximation in optics, which corresponds to a light wave propagating over the z-axis. This is the x-axis here. And when you have suppose a Gaussian distribution of the optical field, all right, which in probabilistic interpretation of quantum mechanics corresponds to the probability of finding a photon. The higher the probability is connected to the higher amplitude of the field. So this Gaussian distribution is the intensity profile of light, but it corresponds to the probability of finding photons over space. So this modulus of psi squared can be properly modeled by some constant squared, modulus squared. You can find out what is this thing. So this is x0 here, and you'll find out that in terms of plane waves, the field, the optical field, corresponds to some amplitude exponential of, with some imaginary factor here, omega t, which corresponds to the frequency of light, minus some k of x minus some k sub z here. So the wave is propagating in the xz plane, all right? So this is the plane wave. This is integrated. This is integrated over all the values of kx and kz. You must integrate over two variables here, and of course the dispersion relation for electromagnetic waves must be applied. But in paraxial optics, your wave vector, which corresponds to some x component plus some z component, is assumed to be something like this. Approximately all the k value, which is omega over c, the k value, which is omega divided by the speed of light, is almost entirely in the z direction. So the k z is, apart from some correction, is almost equal to omega over c, all right? Plus some delta kx in the x-axis. And this corresponds, when you consider plane waves, all the waves are propagating almost parallel to z-axis. All right, all the waves are parallel to z-axis. So if we pick up a Schrodinger equation for a particle, right? So in this approximation, you have a k factor here for a given component of the light. The light amplitude, this is a spectrum, which is some spectrum of k of x and k of z here, but the spectrum must satisfy this called dispersion relation. This k here is almost entirely in the z direction, so there is a component which is almost all the modulus, so the modulus is k, but when you project onto k factor, this is an angle of theta, so kz is equal to k cosine of theta, but this angle is very small, so this is almost k, with corrected to order theta squared divided by 2, and you can neglect this thing here. And kx is just k sine of the angle, but is approximately k times theta. So this corresponds to some Gaussian. You can show this when the partial distribution of the initial optical field at z equal to 0 is a Gaussian distribution. Of course, I am considering just one transverse direction, but if you consider x and y directions, you could model a laser beam by some Gaussian distribution, of course, but this is just a laser beam which doesn't vary in the y direction, but vary as a Gaussian in the x direction. It would be a possible scenario for this analysis. And in this case, you will have that the wave vector is almost entirely in the z direction. This is what is meant by a paraxial. It's almost parallel to the axis of propagation, which is assumed to be the z-axis. So z-axis is the propagation axis. All right, this is the propagation axis. So if all the waves are pointing towards positive z direction with some small variations, which corresponds to some k of x component here, you can find out that time and z is related by the speed of light. So c times t is almost nearly z. All right, it's almost nearly z. So z is equal to c times t, right? Or times t is equal to z over c, right? Remember that for light propagating, many plane waves propagating, but small deviations from the z-axis, almost all the waves will arrive at certain z distance after a time t related by this equation here. The propagated distance z is equal to the speed of light times t. Of course, the velocity here for a plane wave which is propagating in this direction, which is not exactly z, the speed of light corresponds to the entire c in that direction. The speed of light in this direction will be a little bit lower, but in the paraxial approximation, you just approximate things by this equation here. All right. So also remember the following: a photon can be you can attribute to a photon an effective mass, of photon. It is just an approximation because you can use relativistic mechanics. So mc squared is equal to h bar omega, which is h bar c k. All right, and then you'll find out that the mass of the photon is h bar k divided by c. Right? Because you can divide all the equation by c squared. So h bar k divided by c. This is the mass of the photon. All right, and the z relates to time t. Right. This is the paraxial approximation. You must remember that paraxial. Right. So if you apply Schrodinger's equation, I h bar time derivative of the photon field here, you are neglecting completely the polarization of the photon field. It's important because the photon field is always described by Maxwell's equations, even if it's a quantized version of Maxwell's equations, but this is it is an approximation. So if you applied Schrodinger's equations here, you'll have just the derivative over space. You just have x and t. Now you can replace time by z. If you remember, time is equal to z divided by c. This equation will become I h bar, the derivative of psi. Now it's a function of z. All right, d dz, but dt corresponds to c d dz. All right, you can just use the fact that time t is just replace z over c. So this will introduce a factor of c here in the equation. So you are replacing time derivative by partial derivative along the propagation axis. All right, and here you'll find the mass of the photon, which is related to the wave number. which is h bar k over c. So over c you can multiply here, and you'll find out now it's a function of z and x. All right. Notice h bar c squared divided by h bar. You can eliminate the h bar here. The c factor you can eliminate, and you'll find out deep side the z is equal to minus 1 over twice the wave number, second derivative with respect to x and z. And this equation here is the Paraxial Approximation in optics, right? Let me write it in a more fashionable way so you can clearly see. So the wave number plays the role of mass, and the distance z plays the role of time for paraxial wave equation. And this is a very important analogy because make you can simulate or you can emulate quantum mechanical simple quantum mechanical systems using light. And this equation here just allow you to study diffraction effects. So this is optical diffraction and so on and so forth. And you can just pick the evolution of a Gaussian wave packet, which is respective to time, but time and distance for light are just the same thing apart from some constant. And now you can consider as a Gaussian packet of light propagates, it gets smeared. The Gaussian becomes more large and the amplitude diminishes. So also you can calculate for a just a rectangular function or a window function also, and you'll find out for the wave packet of a particle the oscillating patterns, and here you'll find out the diffraction fringes, which is a very well-known fact from diffraction. So if you can consider the psi zero, it's just a window here with respect to x, you can calculate this thing for light waves, and you'll find out the diffraction patterns, and you can calculate for a particle which has a probability in this window, and it will just evolve in the same way. But just for a massive particle, you need to consider time. For a photon, time and z. In the paraxial approximation, to be very precise here, in the paraxial approximation, time and distance, the propagated distance can be related by the speed of light. It is a very, very good approximation, as a matter of fact. This equation reproduces very well the effects of diffraction for light. All right, so this is the optical analog of Schrodinger's equation. All right. Well, this is it. I guess we did the demonstrations here. You can just research by yourself and find in some textbooks the paraxial wave approximation, the effects of diffraction, but uh, this just elucidates some quantum mechanical issues if you understand perfectly the diffraction of light, and makes more clear perhaps some aspects of a ondulatory properties of particles in quantum mechanics. All right, particles in quantum mechanics are described by a classical field which uh, evolves according to Schrodinger's equation in general. For non-relativistic particle, there is a very good resemblance or a very good mapping to a problem in optics. Well, for one space dimension and two space dimensions, if you go to 3 dimensions, perhaps the analogies break down because for light is similar to just having one spatial dimension less because there are constraints related to propagated distance and time. Okay, but that's it. Hope you enjoyed, and next time we'll talk a little bit more about quantum wells, about the infinite well.